Okay, so good morning everyone, and welcome to the May Research Conference. Without further ado, I'm going to call on Zilber to introduce our first speaker.
Thank you. Well, it is a real pleasure for me to introduce Jonathan Pila for this talk today. Jonathan is a member of this institute and logic group, as well as number theory group. And Jonathan, as far as I know, started in mathematics under supervision of Sarnak at Stanford, and was already then developing some interest in logic, and then went on to work with Bombieri, where they introduced the famous counting argument by Bombieri-Pila. And later on, I guess sometime in 2004 or 2003, Jonathan came here in this institute to talk with Alex Wilkie, suggesting a new idea of how to use this argument coming from this Bombieri-Pila, pairing it with ideas from logic, from model theory, and together they developed model theoretic argument in O minimality that now is called Pila-Wilkie counting method. And then later with Umberto Zanier from Pisa, they found a way of, they suggested a way of using this in Diophantine geometry, and since then it was a great success that generated a lot of activity, a lot of work, and got Jonathan, first of all, Clay Research Award. So Clay Institute was the first who spotted the talent, and then there was Senior Whitehead Prize from London Mathematical Society. Most recently, at last, logic community responded to this challenge, and Jonathan, along with a group of logicians who worked on this topic, got the most prized Karp Prize. And well, most importantly, so this activity brought together well, people who work in number theory, complex and real analysis, and even differential algebra. So this links existed before, but this has been a great extension later. And I think maybe the main challenge, well, the main message that Jonathan brought to this community of mathematicians is that it is sometimes really useful to use logic in your research.
Okay. Thank you. Okay, thank you very much for the introduction, and thanks to the Clay Institute for the invitation to speak. Let me see if I can wake up the computer and okay, good. Now let's see if this one works. Okay, that one works too. Good. Okay, so I want to talk today about some themes around Ax-Schanuel's conjecture in transcendental number theory, some analogs, in particular functional analogs, and their connections with certain Diophantine problems. And the O minimality in counting that Boris mentioned will come in very briefly. I'm trying to somehow concentrate here on the Diophantine problems and their origins, somehow their connections with Schanuel's conjecture, well, rather than particular methods. So I want to start with just a little bit to contextualize Schanuel's conjecture, to talk a bit about transcendental number theory, which I guess, well, a convenient starting point is with Hermite, 1873, proving that E is a transcendental number, and then later Hermite-Lindemann, proving that e to the alpha is transcendental for any, that should be a non-zero algebraic number. So that Q there, alpha in Q, that should have a line on top of it. Okay, well, I have the definition there of algebraically independent over Q and of algebraic numbers, which form a subfield of the complex numbers. And at the end of his paper, Lindemann stated, somehow without proof, that by similar methods you could prove this. And later Weierstrass gave a proof of this theorem, Lindemann's theorem, that if you have algebraic numbers which are linearly independent over Q, then not only is each exponential a transcendental number, but those transcendental numbers are indeed algebraically independent. They have no relations over Q. So now I want to talk a bit about logarithms. So one of Hilbert's problems, the problem 7, was to prove this statement, which was, well, the Gelfand-Schneider theorem, that an algebraic number, not 0 or 1, to an irrational algebraic power is always transcendental. And so you have the particular examples, I think, which were the original examples of Hilbert. 2 to the root 2 is transcendental, and e to the pi, which can be viewed as a value of -1 to the I. And Gelfand at least made the conjecture, the kind of dual conjecture to the Lindemann theorem, that if you have algebraic numbers which are not 0 and they're multiplicatively independent, then their logarithms should not only be transcendental, but should be algebraically independent. So that's still open. It's actually not known that any two logarithms are algebraically independent, although they're all transcendental. And the best result that's known is Baker's theorem, that under these conditions, the logarithms are linearly independent over algebraic numbers. So just to mention another line of results in transcendental number theory, so you can generalize the a to the b idea in another direction. So this was also conjectured by Gelfand, that if this beta, now I'm switched from a to the b to alpha to the beta, is algebraic of degree d, then these d-1 powers, alpha to the beta to the j, if you like, for j equals 1 to d-1, should be not only transcendental, but algebraically independent. And, well, he proved this for d equals 3, for d equals 2, it's Gelfand-Schneider. And the best result known there is roughly halfway. Somehow the transcendence degree is a little bit more than half, at least a little bit more than half. So that's just to set the scene for Schanuel's conjecture, which was made somewhere in the mid-60s, that if Z1 up to Zn are complex numbers linearly independent over Q, then at least among the numbers Z1 up to Zn and e to the Z1 up to e to the Zn are at least n which are algebraically independent over Q. So the transcendence degree is at least n, and it's an exercise, actually not a very difficult exercise, that implies all the previous theorems and conjectures and a lot more. For example, the independence of pi and e to the pi, which is a theorem of Nestorenko, and also of pi and e, which is not known. Schanuel's conjecture is known for n equals 1 by the Hermite-Lindemann theorem, but it's open for n equals 2, and it looks to be very far out of reach. So this is the front page of Lang's book. Schanuel's conjecture, somehow it first appeared in print in a book by Lang. It seems that Schanuel was in graduate school taking a course with Lang and somehow came up with this statement. So there I've cut out, I didn't cut it out, I photocopied the page with the conjecture on it, which is in the yellow box. Now, Schanuel apparently also made a conjecture for, corresponding conjecture for functions, which is what I want to describe now. So that conjecture was proved by Ax in 1971. This is the first page of Ax's paper, and this is a theorem that goes by the name Ax-Schanuel. Oops. So Ax-Schanuel now is a theorem about functions. So we take the Cartesian powers of the exponential function, just going from c to the n to c cross to the n. C cross is the non-zero complex numbers. And so inside c to the n cross c cross to the n is the graph of exponentiation. And inside that space, we can also consider algebraic varieties, which are just solution sets, zero sets of some polynomials with complex coefficients. And the question now is, how do v and gamma interact? How does the graph of exponentiation interact with algebraic subvarieties? And this is, well, governed to some extent by this Ax-Schanuel theorem, which I've written in this way. Usually you see this theorem written in the setting of differential algebra, differential fields, but I've preferred to put it in a more geometric way, more geometric formulation. Actually, the formulations are more or less equivalent via, well, they're more or less equivalent. So what does the theorem say? It says that if you look at the intersection of v and gamma, and you take a component of that, then you have this dimension inequality, and this inequality says that the component never has more than the typical or expected dimension. So if you rearrange this, if you like, the codimension of A in this ambient space is just the codimension of V plus the codimension of gamma. They never have a bigger intersection, which is, if you like, saying that the conditions of being on V and being on gamma are always independent. So you never, so that dimension can never be larger than it should be. And in fact, that inequality, dim A less than or equal, should be an equality, really. The dimension of those components can't be smaller. But I put it that way because of the reformulation I want to make. Oh, there's a condition, of course. This dimension can't be of an atypically large dimension unless something very particular happens, which is that A is contained in the translate of a rational linear subspace. Now, that's a situation where in Cn, that condition on Cn remains algebraic under exponentiation. So that's a case where the two conditions can coincide. So another way of saying that condition is that some rational linear combination sum of qi zi is constant on this component, where the q's are not all 0. Now, a way of reformulating this that makes it look like the previous version of Schanuel's conjecture, if you look on A, you have the functions z1 up to zn and e to the z1 up to e to the zn. And then this variety V, which contains A, is then giving you an upper bound on the transcendence degree of those functions. So this is saying that that transcendence degree is at least the dimension of A plus n. That's just another way of saying that, unless the same thing happens. And I want to now focus on a particular special case of this theorem, which I call Ax-Lindemann, because it's somehow the part that corresponds to Lindemann's theorem. Well, and you've got that in the middle there. But let me just, for convenience, we're going to call a subvariety of c to the n, which is defined by linear equations of that form, sum of qi zi equals c, but possibly several such equations, will be called a weakly special subvariety. That's a bit shorter than translate of rational linear subspace. The exponential of such a thing is a coset of an irreducible algebraic subgroup, a subtorus. And so now this Ax-Lindemann theorem is going to tell us something about when an algebraic subvariety in c to the n, when the exponential of that can be inside some proper algebraic subvariety. And the answer is that this can only happen if W, as W is an algebraic subvariety in c to the n. We look at its image under exponentiation, that this can only be contained in something algebraic if W is contained in something in a proper weakly special subvariety. And in that case, indeed, W, the exp of W, will indeed be contained in something in a multiplicative, well, in a coset of the subtorus. It'll satisfy the multiplicative relation. And otherwise, the image of W is Zariski dense in the image. It's not contained inside anything, any proper algebraic subvariety. Now, another way of saying this is to consider, for our W, we take L to be the smallest weakly special subvariety which contains it, and then the image of that will be some coset of a subtorus, and the exponential of W will be Zariski dense in that. And therefore, if the exponential of W is contained in V, so will be the exponential of L, because of this Zariski density property. And therefore, if W is contained if the exponential of W is contained in V, then there'll be this L, which contains W, and whose exponential is also contained in V. And another way of saying that is that if you fix V and look for a maximal algebraic thing inside the exponential inverse image, that thing is always weakly special. So these two formulations are really equivalent, and they're both very special cases of the Ax-Schanuel theorem. Okay, so I want to say very little, a little bit, but really not very much somehow, about model theory of complex exponentiation. The first order theory of the complex numbers as an algebraically closed field is an extremely well-behaved, the first order theory is extremely very well-behaved theory, somehow a model of good behavior. It's complete and decidable theory, and even has stronger properties. But if you introduce the exponential and consider the first order theory of that structure, then this becomes very, very complicated because the integers become a definable set in there. And so you can start talking about the integers. You can do all of number theory. And of course, you get all of Gödel type problems. You get undecidability and so on. This theory is somehow not nice. But Boris Zilber showed that if you move to a suitable non-first order formulation, then you can somehow fix the integers. You can contain the trouble, if you like, that they cause. And you can make a model theory in a certain non-first order setting and create something that looks, well, you can create a theory of an algebraically closed field, characteristic 0, which has an exponential satisfying Schanuel's conjecture and some other properties, and which is very well behaved. And this has led to a lot of very interesting work comparing the complex numbers with its exponential to, well, Boris's exponential, the Zilber field, the Zilber exponential. And in the course of his work on this, he formulated a Diophantine conjecture, the CIT, which I want to explain first in the context of C cross to the n. So this comes by considering a certain stronger version of Schanuel's conjecture. So here is another way to formulate Schanuel's conjecture. Schanuel's conjecture says that the transcendence degree of some set of numbers is at least n, and that means that such a set of numbers can't be contained in a variety of dimension less than n defined over Q. So we take V, an algebraic subvariety of C to the 2n defined over Q and of dimension less than n. And the statement now is that if you get a point of the form z1 up to zn, e to the z1 up to e to the zn on that graph, then the z's must be dependent, linearly dependent over Q. That's a simple restatement of Schanuel's conjecture. But now Boris formulated a uniform version of this where you take your V in exactly the same form, but now the postulate is that somehow for this V, there's actually a finite set of such rational relations that somehow control all the points. Now, you have to be a bit careful how you formulate that. You need to allow these powers, these shifts by 2 pi I k, but it's essentially a finiteness statement. In the first statement, you just say every point on there of the form z e to the z is accounted for by a rational relation. And now we want to say that given V, there are somehow essentially finitely many rational relations that account for everything. So this is a stronger conjecture. So of course it's still open, but Zilber showed that this has an implication just in the world of algebraic geometry. So I want to go through this. I apologize that the slide is a little bit dense. I guess it's a quite simple dimension computation, and I decided it would be best all kept on the one slide. So we've got a V in C to the n cross, well, C cross to the n. And we can consider its image on the second factor. It just has a projection, which is some new algebraic subvariety now of C star to the n. And this projection has a certain generic dimension. So it has a certain dimension of the fibers outside some proper subvariety. And now we suppose we've got a tuple on that of the form z e to the z. And therefore, on Schanuel's conjecture, this z lies in a rational linear space. And indeed, the dimension of that linear space will be precisely the linear dimension over Q of the z's. And we take T to be its image. Under exponentiation, that's a multiplicative subgroup. And it has the same dimension, because that exponential map is locally one-to-one. And now Z then, the exp of Z belongs to some component of the intersection of T with W. And we're going to make a dimension computation. So on the one hand, the transcendence degree by Schanuel is at least the dimension of T, which was the same as the dimension of L. We're on this first full red line. But e to the z belongs to this algebraic component A, where the fibers have dimension d. So the transcendent belongs to something algebraic whose degree is at most d plus dim A. And d is dim V minus dim W. That's because it's the dimension of the fiber. And dim V is less than n, because that was our assumption on V. And so the conclusion, if you rearrange all of this, is that this A has an atypically large dimension. The dimension of A exceeds what you'd expect if the conditions on T and W were independent. So this exp of z lies in an atypical intersection. So this led Zilber to make the following conjecture, which now there's no exponential, the exponential function is somehow in the background. This conjecture only concerns algebraic subvarieties of C cross to the n and algebraic subgroups. So this is the CIT, and it has also it has two sources really, this, in the work of Zilber and in the work of Bombieri-Massezania, which we'll say a little bit about in a minute. That let W be a subvariety of C cross to the n, then there's a finite set of proper irreducible algebraic subgroups, or proper algebraic subgroups, such that any atypical component of any intersection of W with an algebraic subgroup is contained in one of those. There are somehow finitely many reasons for atypical intersections. And Zilber showed that this CIT is somehow the difference between Schanuel's conjecture and its uniform version. So SC plus CIT implies USC, and USC implies the other two. So this conjecture is open in general for the dimension of W at least 2, but it is known for curves. So I want to state that and see what that result says. Now, if you have a point on if you have a curve that's dimension 1 in C star to the n, then a point on this curve is atypical if it lies in an algebraic subgroup of codimension 2. In other words, if it satisfies 2 independent multiplicative conditions. And the curve itself is atypical if the curve itself is contained in a proper algebraic subgroup. And those are the only possibilities for curves. The only subvarieties are points in the curve itself. So, and in this case, one has the following theorem of Morin over Q bar and Bombieri-Massezania over C. And this affirms the CIT for curves, that if you have a curve which is not atypical itself, then there are only finitely many atypical points. And a very special case of this would be a statement like the following, which is modeled on some examples given by Bombieri-Massezania. You might consider a curve which is just parametrized in this way, it's the set of points 2, 3, t plus 1, t squared plus 47 for some complex t, parameterized by t, then there will only be finitely many t's for which you get two dependencies. So for example, you can see if t is 1, well, 1 is dependent, but also, so t equals 1 is a root of unity, so that's dependent. T plus 1 is 2, which is dependent on 2. If you put t equals 8, then 8 is multiplicatively dependent on 2, and 8 plus 1, which is 9, is dependent on the 3. So they'll, and if you put t equals 9, I've arranged it anyhow. I arranged it that t is 9, and t squared plus 47 is 128. So there'll be finitely many t's. And you'll see, I just want to go back there. So we allowed, in particular, you notice that I allowed these 2 and 3, these constant coordinates on the curve, which means in particular that there are only finitely many t's for which the non-constant things are dependent on the 2 and the 3. In other words, in the division group generated by 2 and 3. And more generally, this means that this conjecture implies the Mordell-Lang theorem in this setting. So that's a theorem that if you take a curve, let's say a plane curve for simplicity, and you take any fixed numbers, a1 up to ak, and you look for points on the curve which are in the division group generated by the a's, which is I've defined up there, then this is, you only get finitely many points for curves. That's a theorem of Liardet from 1974, but it's somehow part of the Mordell-Lang series of problem conjectures and theorems. And indeed, so I'm going to put those up just briefly to make that connection, but we don't, I mean, that's just somehow for, we don't need to, and I don't want to dwell on the statements there, but indeed the CIT implies Mordell-Lang and is a very far-reaching generalization and is open, where Mordell-Lang, of course, is a theorem. So here is, okay, so I want to connect with the line of problems that began with Mordell's paper of 1922, where he stated the Mordell conjecture. And then Lang in the 60s started to reformulate this in terms of, well, in the terms that we'll see on the next slides. So the initial problem, which appears, I think, even in that paper of Lang, which I just had up and was solved by Ihara, Ser, and Tate, that if you have a curve in the plane and you look for points on it which are roots of unity, then there are only finitely many such points, unless C has a very particular form that it has, has the form given there, that it's defined by a multiplicative equation, x to the n, y to the m, root of unity. And if you take the higher dimensional version of that, so-called multiplicative Manin-Mumford, which became a theorem of Mann on Laurent, and if you replace C cross to the n by an abelian variety, then you get the Manin-Mumford conjecture, as it was originally, came to be formulated and proved by Raynaud. And of course, this became part of the Mordell-Lang, proved by Faltings. And then, gradually in somehow more general versions. So this is all implied by CIT in the semi-abelian version. But CIT goes much further. So, okay, so next I want to talk about an analog of these problems in particular an analog of the Manin-Mumford conjecture, something called the Andre-Oort conjecture, which is something formulated for a Shimura variety, which is a kind of certain type, well, of algebraic variety, moduli spaces. They all arise as certain kinds of arithmetic quotients, and we'll see a few examples. But before the examples, I want to concentrate on the formulation, which is exactly modeled on the Manin-Mumford conjecture. So when you have such a variety, it comes equipped with a collection of so-called special subvarieties. And these are the analogs of multiplicative subgroups. They're somehow a collection of subvarieties which are naturally associated with the structure on X. And in particular, there are zero-dimensional ones called special points, which are the analogs of torsion points. And now we have a conjecture which is exactly the analog of Manin-Mumford, that a subvariety of a Shimura variety contains only finitely many maximal special subvarieties. In other words, that there are finitely many such special subvarieties. So the simplest version, which I'm going to explain in a bit more detail, was proved by Andre in 1998. This is when X is C squared as a Shimura variety, which I'm going to explain. That's an unconditional proof. And then a full proof of this conjecture under the GRH was given in work, well, starting with Edixhoven, but completed by Klingler, Ulmo, and Yafeev. And in the last few years, somehow this method that Boris mentioned of O minimality and point counting has enabled some further unconditional cases. But so I want to talk about C as a Shimura variety. So here, the background here is elliptic curves and their moduli. So when you have a lattice in the complex numbers, then the complex numbers modulo the lattice is an elliptic curve. And we can always normalize this lattice to be generated by 1 and tau. Tau is in the upper half plane. And in that case, the elliptic curve that you get is determined up to isomorphism over C by its J invariant, which we can use to define a function on the upper half plane, the J function, which sends tau to J of tau. So this is a holomorphic function on the upper half plane. And just to mention some basic arithmetic properties, it's invariant under SL2Z, acting as fractional linear transformations. On the other hand, and it's a transcendental function, but if you take J of tau and J of G tau for any rational 2x2 matrix with a positive determinant, then those two functions are algebraically dependent. They're related by a polynomial called a modular polynomial. And okay, so there's a picture now, but I just want to mention that the special points in C are the J invariants of elliptic curves with complex multiplication, which are just the images of quadratic points, the J of tau for tau quadratic. So here's the, well, classic picture of the fundamental domain. The classic fundamental domain is the gray one, and its images under SL2Z. So these are the symmetries of the J function. And here is one example of a modular polynomial. So if you take J of tau Z as X, and J of 2Z, which is Z operated on by this 2x2 rational matrix with a positive determinant, then x and y are algebraically related by the modular polynomial phi2, and that is phi2. Now, for the J function, you can also formulate transcendence conjectures, which are the analogs of Schanuel's conjecture. And somehow the big picture here is given by something called the Grothendieck-Andre period conjecture. But I just want to say a couple of things about J. So the analog of the Hermite-Lindemann theorem is the statement, it's a theorem of Schneider from the 30s, that the only algebraic numbers for which J of alpha is also algebraic are the quadratic numbers. And then you would have a conjecture, which, if you like, is a modular analog of Schanuel's conjecture. It's not a quite full analog in a certain way, that if you take numbers in the upper half plane, and if they're not quadratic, and if they're in independent orbits under GL2Q plus, then the transcendence degree should be at least n. But this is also open conjecture. And in this case, not even the Lindemann case is known. It's if the alphas are algebraic, well, it's not known. So what about C squared as a Shimura variety? So this, we view it as the moduli space of pairs of elliptic curves up to isomorphism over C. And the special subvarieties come in dimensions 2, 1, and 0. In dimension 2, you have X itself. In dimension 0, you have the special points, which I mentioned. And in dimension 1, you have modular curves and horizontal and vertical lines on a special coordinate. And then Andre's theorem says that if you have a curve in C squared, which contains infinitely many special points, then this must be a special curve. It must be a dimension 1 thing from that list, either a modular curve or a horizontal or vertical line on a special coordinate. So this was proved by Andre in 1998. There was an independent proof by Edixhoven on GRH. And very recently, so Andre's proof was unconditional but ineffective because it depended on certain lower bounds in analytic number theory. Very recently, this theorem has been reproved effectively, independently by Kuna and Bilu Masuzanya. And this is, at this point, still the only case of this theorem which is known effectively.
Can you just, in this case, specify what special points and special curves are?
Yeah, that's here. The special points.
Special points, J0, J1, J0, J2.
Yes.
Special. I'm a bit specialized now.
Yeah, so the special points are the points J0, J1, where J0 and J1 are the J invariants of elliptic curves with Cm, or if you like, they are the images of quadratic points. J0 is J of tau naught, and J1 is J of tau 1, where tau naught and tau 1 are quadratic points. So that's when the lattice has a quadratic generator, that's the condition under which it allows extra symmetries. And then the curve also inherits these extra symmetries. Yeah, so does that help with the, yeah, the word special is, well, the problem is it becomes a bit generic, but in a way, but okay, since now I can throw x equals c to the n at you with this is as a Shimura variety. And there's a description of the special subvarieties. They're just the hybrids of what happens in C squared. You take any mixture of conditions, you impose modular conditions on some coordinates, and you impose other coordinates to be fixed and special. Then you get some subvarieties that may be reducible, but you take irreducible components, and those are the special subvarieties. Special points are n tuples of special points in C. And we'll also need this notion of weakly special subvarieties where you allow constants to be arbitrary and not special. So that's x equals c to the n. And just another example of the kind of paradigm Shimura varieties are the moduli spaces of abelian varieties. And the special points there are, again, the CM, the ones with the maximal amount of complex multiplication. And in this context, so this is conjecture formulated, I guess, by Pink, independently of the other developments, formulated a conjecture in the same spirit as the CIT, that if you take a mixed Shimura variety, which is a slightly still more general object, and a subvariety of that, then there are only essentially finitely many reasons, reasons for this, that this variety intersects a special subvariety atypically in dimension. So this is the definition that is, you define this notion of an atypical component is one which is a component of an intersection of V with some special subvariety such that the component has dimension too large. And then the conjecture is, the Zilber-Pink conjecture, that there are only finitely many maximal such things. So this, if you like, has the three sources of independent sources of this conjecture. And you can view it, again, in terms of a uniform Schanuel conjecture. You can view it as the difference between a Schanuel and a uniform Schanuel. But it's now a very general Diophantine conjecture that includes all of the conjectures, all of the Diophantine conjectures mentioned up till now, the Mordell-Lang family and the Andre-Oort, but also much more general statements about, for example, analogs of the Bombieri-Massazania theorem for curves and so on. So this is a very, very far-reaching conjecture, and it's sort of, on the one hand, a sort of a unified statement, but it has very many different faces. The Mordell-Lang sort of aspects and the modular aspects, and it's somehow being studied in very many different ways. But I want to mention briefly somehow the approach to these problems via point counting in order to get back finally to functional transcendence analogs. So this is a strategy which was proposed by Umberto Zagna in the context of the Mann-Mumford giving a new proof of Mann-Mumford. And this is, so I've renormalized the exponential function. Now I made it e to the 2 pi I z, so that the pre-images of torsion points are now rational points. So now if you take your variety V and C star to the n and you look for torsion points, then instead of this you can pull back under the exponential function and you can go looking for rational points. And of course the exponential function is periodic now under z to the n, translations by z to the n. So in fact it suffices to look in a fundamental domain for that action. So you can go looking for rational points on this set Z, which is the pre-image of V intersected with the fundamental domain. And the strategy now is to play off a lower bound coming from Galois conjugates against an upper bound coming from the counting theorem of rational points on such sets. So this set Z is an example of a definable set in an O-minimal structure, which I don't want to go into. This is a notion coming from the model theory of real exponentiation and developed in work of Van den Dries, Pila, and Steinhorn initially. And so here it is, you play off lower bounds against upper bounds. So the point is that the roots of unity have rather large Galois orbits. So if V, which we'll assume defined over Q for simplicity, contains one such point, it will contain the whole Galois orbit, and that, for a root of unity of order t, is nearly t points, and they'll have a certain height. That'll give you points whose height is at most t, and you'll get 2 of them on this set Z, and you play that off against an upper bound, which comes from this point counting on definable sets. But this upper bound, I've written it there, but I've put a Z asterisk, and this asterisk means that this counting theorem only applies to Z once you've removed algebraic subsets. And so this method, and I mean somehow, I know I've gone through it sort of very briefly, only to get to this point, that it comes down to understanding what are the algebraic subvarieties inside that pi should be an e to the minus 1 of v. You need to understand what's algebraic in there, and the answer is given by Ax-Lindemann. And with that information, you can carry through this proof. In this case, it would give you a new proof of this theorem I had up of Laurent-Mann, the multiplicative one in Mumford. But you can replay exactly the same proof with the J function, and indeed with other Shimura varieties. So I guess I need to finish in a couple of minutes. I won't go through this, but it's exactly the same proof. So you play off lower bounds against upper bounds. Now you're looking for quadratic points. The lower bounds come from arithmetic. In this case, it's the theory of complex multiplication, classical theory initiated by Kronecker in the 19th century, and then this Siegel, lower bound for class numbers. So these very classical things. And just before getting back, so the key thing I want to get to is the Ax-Lindemann statement. But in fact, this method can be carried out, has been now carried out in a number of cases. And in fact, I think it's fair to say now that everything is there or almost there except for the Galois lower bounds. The arithmetic there seems to be very challenging. So there, the Zimmermann has established these Galois lower bounds for AG up to genus 6. And then the rest is the other ingredients you need are somehow in place. So one can prove further cases of Andre-Oort. But the key thing I want to get to is the Ax-Lindemann statement. So this, if you like, is a functional, well, it is a functional transcendent statement for the particular Shimura variety, and for the J function, it tells us when the image of an algebraic subvariety W, when the image of that under J is Zariski dense in C to the n. Now I need to explain that H to the n, the upper half plane to the n, actually there are no algebraic subvarieties contained in there. So by W, so by an algebraic subvariety of H to the n, I simply mean that you take an algebraic subvariety in the ambient C to the n, and you intersect it with H to the n and take a component of that, analytic component, that the image of such a thing is Zariski dense unless this W satisfies either a modular relation or some coordinate is constant. In other words, the image is Zariski dense unless W is contained in something weakly special. And the more general statement in a general Shimura variety takes the same form. So this, well, this theorem is now established in the work of various people. But this Ax-Lindemann itself should be a special case of an Ax-Schanuel conjecture, and that was my finishing point, that there should be an Ax-Schanuel, or there is at least a conjecture that should govern the interaction of the graph of this uniformization of any Shimura variety with algebraic subvarieties. And this kind of theorem now has been approached in very many ways. differential algebra is in the original Ax, and monodromy, ominomality and point counting, complex geometry, this very natural statement on the one hand, and on the other hand, it should be, or could be, instrumental in proving further cases of this Zilber-Pink conjecture, provided you have some other ingredients. Okay, so that was the story that I'd like to stop there. Thank you.